Alright, so good morning students once again. Just a very quick recap of what we studied in our previous session. Okay, so we just discussed about the working principle of a very important power device which is called as silicon controlled rectifier, right? In short, it is also called as SCR. Okay, the main difference between a normal rectifier and a silicon controlled rectifier is that a normal rectifier doesn't have any control terminal, right? You just have an anode and a cathode, whereas in the case of a SCR you have a dedicated third terminal which really controls the entire operation of the rectification process. Okay, however, with respect to the characteristics, a silicon controlled rectifier has completely different characteristics. Okay, although it can be used for mainly switching purpose itself. Okay, so we had just gone through some of the basics, the symbol, the layered structure, and the split up with respect to the construction and also the circuit wise. Okay, basically an SCR is a combination of two transistors, wherein one transistor is of PNP and the second one is of NPN transistor. Okay, and we had seen in detail in the last session why an SCR, once it is turned off, cannot be turned off in a natural process. Okay, so if you want to turn off a SCR, you will have to forcibly turn off using two processes, wherein the first one is called anode current interruption and the second one is forced commutation. Okay, so only by using those two principles you can turn off a SCR. And coming to the characteristics, okay, let me spend 30 seconds of time on it again, because the next devices that we are going to discuss in this particular session, they are in some way related to this SCR itself. Okay, right, so in the last session we had seen that in the first quadrant an SCR behaves like this, okay, as it is shown in the slide, right? So this particular region is called as forward blocking region, wherein the SCR is off. Okay, and this is a stage in the characteristics where there is a sudden reduction in the voltage across the junction of the particular SCR, wherein it is completely reverse biased. It is only after this particular stage that there is a sudden increase in the current, right? So we say that in this particular stage the SCR is on. Okay, so you can switch on and switch off a particular SCR in the forward bias characteristics itself, okay, by using a gate. Okay, so if you just go on increasing the gate current, then the forward breakover voltage keeps on reducing, okay, which is clearly visible here, right? Then in the reverse bias characteristics, an SCR behaves absolutely normally like a general reverse biased PN junction. Okay, fine. So with this background, let us try to understand the next device, which is called a diac. Okay, a diac is basically a diode alternating current. Okay, its full form. So it's basically a two-terminal parallel inverse combination of semiconductor layers that permits triggering in either direction. So there are many keywords involved here, right? So we'll try to break them and then try to understand. Okay, but just to go through some of the important points, it says that there is a breakover voltage in either direction. So this point is extremely important for us. In the case of SCR, we had a breakover voltage especially in the forward characteristics, right? Okay, which means if I just consider if I just plot it, the SCR behaved like this. Okay, so wherein this particular stage is called as forward breakover voltage. right? uh, Now what if we obtain a similar characteristics in the third quadrant also, right? Okay, so that would be really wonderful, right? So the possibility of an on condition in either directions can be used to its fullest advantage, especially for the AC applications. Okay, so the point is, if somehow we are able to obtain the SCR characteristics even in the third quadrant also, then that particular graph can be used especially for the AC applications. So what does the basic arrangement reveal? Okay, it says that the basic arrangement of a semiconductor layers of a diode is as shown. So I'll just go through that slide. You can just observe it. So that's the basic construction of a particular diode. A diac. So you have two anodes, anode 1 and anode 2. Surprisingly, there is no gate terminal here, so we do not have any control of it, right? So we'll just try to understand why do we get this particular characteristics. Okay, then instead, so there is an anode 1 and anode 2. Alright, when anode 1 is made positive with respect to anode 2, the semiconductor layers of the particular interest are P1, N2, P2. Okay, alright, so we'll be looking at these things in detail. But before that, let us first try to understand some basics which will really help us in understanding a diac in a much better way. Okay, so what we will do is we'll try to take two diodes. Okay, simple diodes. So this is diode 1, right? And let me take another diode which is placed like this. Okay, so let me call this as diode 1 and diode 2, and for this particular combination let me apply an external bias in this way. Okay, so that this will be positive and this will be negative. Okay, basically I am trying to apply an external battery supply. So what will happen if I just increase this particular supply? Let me call it as V. Okay, so whenever I apply an external voltage V, diode D1 becomes forward biased. Okay, so let me write it as FB. FB stands for forward bias. But what will be the status of diode D2? It is reverse biased, right? Because I am applying positive voltage to the cathode of diode D2 and negative voltage to the anode of the diode D2, right? So altogether what happens? Will there be any current flow? No. Okay, there is absolutely no current flow. So let me say that there is no current flow, so this entire thing is still off. Okay, however, what may happen if I just go on increasing the supply voltage from maybe 5 volts, 10 volts, 50 volts, 100 volts. Okay, in such case, anyhow this diode D1 will be on, right? Because it will be conducting. Now this diode D2 undergoes breakdown. Okay, hope you can just correlate the working principle that I had explained in the case of SCR in the previous class, right? As the reverse bias just goes on increasing, at some point of time it has to undergo breakdown. So when that breakdown happens, there is a sudden surge in the reverse current, huge current flows, right? So that it just acts as if it is a short circuit. Okay, so altogether I can say that there will be a current flow, right? So this I can replicate whatever I have just explained with respect to the circuit. I can replicate it in the form of a graph. Okay, so if this is the voltage which I am applying and if this is the current okay, so initially the same thing happens as it is in the case of SCR. very small current. Okay, this current is only due to the minority carriers. Okay, please note it. And as V increases, the voltage across the depletion region, there will be a sudden drop, right? And this is at this point of time there is a sudden surge in the current. Okay, so that is just due to the SCR action. Now the same thing can also be done either way. Okay, what if I just reverse the polarity? Okay, now I'll just change this. So instead of applying the battery in this way, I'll try to apply the battery in a reverse way, so now it is like this, negative, positive. So in such case, diode D1 will be reverse biased and the diode D2 will be forward biased. So it is exactly the opposite of the condition that we had considered in the previous case. Okay, so if I apply a polarity like this, so let me just call it as VF and VR. So when I am applying VR, again I will be getting the characteristics like this: small minority carrier current, and then the drop across the depletion region, and then there is a sudden surge in the current. Okay, so in doing so, what have I obtained? I have obtained, see, just consider this case. Here the device is on, here also the device is on. Okay, so in either direction, depending upon the polarity of the external battery, I am trying to switch on the diode. Okay, then here the diode, in the sense I am talking about the combination of both the diodes. Okay, so the same principle is being used in the case of a diode, a diac. Okay, so this is one diode and that's the second diode. Okay, that's the first connection. The second connection, you can call it as anode 1 and this is anode 2. Okay, so that's the symbol of a diac, which enables the current flow in both the directions. However, there is a drawback here, and the drawback is you cannot control the current flow. For example, what if you want the current flow only in the first quadrant, or what if you want the current to flow only in the third quadrant, right? So the controlling is not possible here. However, there will be current flowing in both the directions, right? So with that basic concept, let us move forward and try to understand. Yes, so this is the characteristic. Depending upon the structure of the particular diac, you will be getting the current like this. So either it is as shown in the slide, or it will be like this also. Okay, it actually depends. Further, so just look at the symbol of a diac. So you can easily observe that it's a combination of two diodes. Okay, so with respect to structure wise, how will the combination of two diodes look like? If I just combine a diode, two diodes, then I'll be getting a 3-layered structure, right? See here, if this is one PN junction, and to the same junction if I add one more layer which is of PNP, okay, then it resembles the structure of a transistor. Okay, so you can use this particular structure as a diac, or you can convert an SCR itself, improvise it, and then convert it to a diac. Okay, so in your textbook what they have done is they have converted the structure of a SCR and then converted to a diac. Okay, so we'll try to go through that particular structure here, so which is shown here. Okay, what I'll be doing is I'll just cross mark it, right, so that I'll be getting two SCRs, right? Students, hope you can observe this. One structure is like this: P N P N. Okay, this is if I say this is anode 1 and anode 2 current. Okay, so just observe. So this is when anode 1 is being made positive, this particular structure is effective. Okay, when anode 2 is being made positive, then this particular structure works. So it is again P N P N. Okay, so there are 4 layers which work at a time. So altogether you can say that there is a current flow in both the directions. Okay, so just look at the symbol of this. The current is flowing in both the directions. So what are the applications of a diac? Diacs are mainly used in AC switches. Okay, wherever there is a need for bidirectional current, there you can think that the diacs are used, right? So they are mainly used in AC switches. Then in the dimmer applications, okay, basically the LED based applications, wherein you'll just notice that the intensity of the light is being continuously varied. So there diacs find the applications. Then in some of the starter circuits, especially for the fluorescent lamps, there also we use the diacs. Okay, alright, so with this let us try to move forward to another device which is called as a triac. Okay, so the fundamental difference between a diac and a triac is that in the diac you don't have a control over the switching action, right? Suppose if you want the current with respect to only anode 1 or with respect to only anode 2, that control is not present in the case of a diac. Okay, however in the case of a triac you can very clearly, precisely have that control. Okay, yes, so what is the definition of a triac state? The triac is fundamentally a diac with a gate terminal for controlling the turn on conditions of the bilateral device in either directions. Okay, so it's very clear and very straightforward. Okay, diac plus a control terminal, I'll just write it, diac plus gate control becomes a triac, as simple as that. Okay, so for either direction of the gate current, the controlling action of the device is in a similar manner to that of a SCR. Okay. The characteristics, however, of a triac in the first and the third quadrants are somewhat different from those of the diac. Alright, next, okay, so let us just go through the holding current. So that's the symbol of a triac, and these are the different variants of the commercially available triacs. Okay, so now let us just look at the construction of a triac. Okay, basically a triac, so how many different layers are there? Let us just go through it. So this is 1, 2, 3, 4, 5, 6 and 7, right? Now if you just refer some other textbooks, you will find that triac, it consists of 6 layers. Okay, wherein the core structure, gate, okay, it has 1 layer occupied, and the anode 1 and anode 2. Okay, so this is anode 1 and anode 2. Okay, so altogether we have 1 layer, 2 layer, 3 layer, and other 3 layers for the structure. Other 3 layers for the internal structure. But what about the extra layer, okay, additional layer? Because here the total number of layers are 7. Okay, so students are not supposed to get confused. The only intention of adding one more layer is just to showcase that the gate can either be connected here or it can be connected here. Okay, that's it, right? So if you combine them, it becomes a single layer itself if you join them, right? So if that is done, then the complete structure, okay, gets converted to only 6 layers. Okay, fine. Now in simple words, how does the operation happen? Because finally there should be the current flow through Pn itself. Okay, so now let us just assume if this gate layer is made positive. Okay, for example, if this is made positive, then this particular layer will be inactive because this particular layer of the gate will be active, right? Then if I want the characteristics in the first quadrant, then anode 2 must be made positive. Okay, so when anode 2 is being made positive, then the current will be flowing through this direction. So it is P N P N. Okay, hope students can understand this. I repeat, the gate at layer N3 is made positive or active, so that this particular layer is again inactive. Okay, inactive in the sense it doesn't add in any way to the current flow. Okay, now anode 2 is being made positive, then the current flows, the direction of the current will be through PNPN region. Okay, now similarly, if you want, or if anode 2 is being made negative, okay, then the current will be flowing in this direction, PNPN, and then out of the device. Okay, so as simple as that. Alright, so that was the working principle of a triac. Okay, so I suggest the students to go through the textbook. You can also Google some other videos of diacs and triacs. Okay, so that you can get some more basic information of the working principle of a diac as well as the triac, right? Okay, then moving forward. Alright, so we are left with one more device, which is called as unijunction transistor, right? Before we go through the working principle of unijunction transistor, let us first highlight upon one important point which is related to a transistor. Okay, whenever we say a transistor, okay, what we mean is that there are 3 layers, okay, in a transistor. It could be a combination of PNP or NPN, but the point is there are always 3 layers. And what about the junctions? There are always 2 junctions. Okay, so this is in a normal transistor, normal bipolar transistor. Okay, but with respect to the power devices, there exists a special device which is called as uni-junction transistor, in the sense just by using a single junction, okay, a junction that actually exists between P and N region, you can obtain a transistor action. Okay, so now this is something special. Now how it can be done? Okay, let us look at the construction of a uni-junction transistor. Alright, so the slide clearly shows you the construction of a uni-junction transistor. So what all components are present? Well, you have a aluminum rod, okay, it's a metal, right? Okay, so this actually acts as the emitter terminal of a uni-junction transistor, and there is a N-type silicon material, okay, the blue colored region shown here. It's a N-type high resistive silicon slab. Now at the junction, I repeat, okay, there is a junction in between the aluminum metal rod and the N-type silicon, and this is the only junction that exists in this particular device. So since it is the only junction, it is called as uni junction. Okay, uni means a single, right? So it is uni junction transistor. Now the point is, how does this particular structure act as if it is a transistor? Okay, so let us just have a look at it. Now below the silicon slab you have two layers, okay, which are actually the ohmic base contacts. Okay, now one important point to be observed is, just note down the position of this particular aluminum rod on this particular N-type silicon slab. It is not exactly at the center, right? It is, you know, more nearer to one end of the slab, and it is farther away from the other end of the slab. Okay, this is just to create a difference in the internal resistance, okay, which in turn helps in the functioning of this particular device as a transistor itself. Okay, so that's a key difference here. Alright, so further, these two ohmic base contacts are being, you know, supplied with external voltage, which is called as VBB. Okay, so we have two bases here, B1 base and B2 base, right? Please note that in a normal transistor the three terminals were emitter, base and the collector. However, in the case of a UJT, you have two bases, B1 and B2, and there is no collector, and we just have a emitter. Okay, the emitter is made up of aluminum rod, okay, and the junction is in between aluminum rod and the silicon N-type slab, and the two base regions are of ohmic contacts. So these two are ohmic contacts. Okay, so can I draw electrical equivalent for it? Yes, students. What might be the electrical equivalent of this particular construction? Okay, so we'll just look at it, but before that, some more important points about this particular structure. Okay, so what are the points? A slab of lightly doped N-type silicon material has two base contacts attached to both ends of one surface and an aluminum rod. Okay, so this is what I just explained. Further, the PN junction of the device is formed at the boundary of the aluminum rod. Yes, okay, so that's the boundary of the aluminum rod. Okay, so here there is a PN junction formed. It is called as uni junction. The single PN junction accounts for the terminology uni junction. Okay, then the aluminum rod is alloyed to the silicon slab at a point closer to the base 2 contact than the base 1 contact. and that the base 2 terminal is made positive with respect to the base 1 terminal by VBB volts. Okay, that's what it is being told here, which means the base 2 is being made more positive with respect to the base 1. So this base 1 is relatively negative with respect to base 2. Okay, fine. Then so how does the circuit look like? It is shown here. Note that the emitter leg is drawn at an angle. Okay, so just observe this emitter. So it is, the symbol is slightly tilted, right? Okay, at some angle. Why? Because this particular aluminum rod's position is exactly not at the center. Okay, it is slightly aligned here. Okay, it is more closer with respect to the base B2 when compared to base B1. Okay, so because of that, with respect to the circuit, symbolically it is shown to be aligned. Okay, fine. So the emitter leg is drawn at an angle to the vertical line representing the slab N type of the material. Fine. The arrowhead is pointing in the direction of the conventional current, which is due to hole flow when the device is in forward biased, active or conducting state. Alright. So let us just try to convert this particular structure to its electrical equivalent. Okay, and then very quickly discuss the characteristics of a UJT. Okay, what I'll do is I'll just go to the previous slide itself, and then I'll try to draw its particular structure. Okay, I'll start from the emitter side. Okay, so that's the emitter. There is a junction between aluminum rod and N-type material, right? So, and it's a PN junction. PN junction in the sense it's a diode, right? So that's a diode. Okay, I just erase this so that it will be easy for us to understand. So that's the emitter, and this is the PN junction diode. Okay, I am talking about this particular region. Now this is followed by two base regions wherein there is resistance associated, right, between these two things. So let me just denote those resistances, right? So this is RB2 and this is RB1. Okay, and here I am applying a voltage VBB. Okay, this is with respect to the ground, right? Okay, and since there is a diode, there is always voltage drop across the diode. Fine. Now how can I obtain the transistor characteristics? Okay, see, the transistor characteristics in the sense this particular unijunction transistor should get switched on and switched off. Okay, so then that means there should be some switching condition. Okay, so how do we obtain it? See, now what if I just vary this particular resistance? Okay, so how do I do that? If I want to obtain the voltage across the resistance RB1, okay, let this be voltage across the resistance RB1. Okay, so let me call it as VB1. So how do I get it? Well, BV1 can be obtained like this. Okay, using the voltage divider formula, it is VBB, right, multiplied by the resistance RB1 divided by RB1 plus RB2. Okay, I am applying the same voltage divider rule, right? Now the ratio of the resistance, let me indicate it by a simple symbol. Okay, maybe neta. Okay, so then it is VBB to neta. So VB1 is being represented by this particular expression. Okay, now the voltage which is appearing at the emitter side, okay, if the emitter voltage right? So let me call this as VE. Okay, if VE, I'm sorry about this line. Okay, all right, let me just write it. So if VE is lesser than the drop across the diode plus VB1, right, then the UJT is off. If VE is greater than VD plus VB1, then the UJT is on. Okay, so we have got two conditions, one when the UJT is off and the another one when the UJT is on. Okay, so that actually depends whether the voltage which is appearing at the emitter side, okay, is it lesser or is it greater than the combination of the voltage which is appearing across the diode as well as the combination of the base resistors. Okay, so depending upon that, we will be getting three type of characteristics. Okay, so the first is when all right. Okay, so this is IE versus VE. Okay, so just look at the parameters, right? So this is the current. Okay, please don't confuse it as voltage, right? So this is the current and this is the emitter voltage. Okay, so if you are getting confused, then you can just interchange the parameters. I don't know why the author has actually put up the graph like this. Okay, it should have been the other way, but anyhow, no problem. So you can very clearly observe that there are three regions. The first one, you have a cutoff region, and the second one, which is quite strange, okay, there is a negative resistance region here. Negative resistance in the sense, as the voltage increases, okay, the current is reducing here. Okay, hope you can understand. As the voltage increases, the current is reducing. Okay, so that is called as negative resistance region, and beyond that you will obtain a valley point. So after the valley point, it's completely saturation region. Okay, now the point is, where do we have the active region? Okay, well, active region is exactly in between that of the cutoff region and the saturation region. So this blue color shaded region represents the active region. Okay, now the point is, similar to our normal transistor, we have got all the three regions: the cutoff, the active, and the saturation region. Okay, so in the cutoff region, the current is very small. Okay, you can just notice the current, it is extremely small. So practically we can say that the current in the cutoff region is almost zero or very small, right? So here it is increasing in the cutoff region, and then finally it will just saturate. Okay, students have to correlate, okay, this like this, right, where this is the voltage and that's the current. Okay, if I just replace them, then the graph also gets reverted. Okay, so that you'll be getting this type of characteristics. Okay, fine. So that was all about a unijunction transistor. Excuse me. So to summarize, we discussed the basic working principle the construction and the characteristics of three important power devices today. The first one being a diac, the second one is a triac, and the third one is a unijunction transistor. Okay, so all these three devices are important with respect to your syllabus. Okay, so just consider that these three topics are important. Okay, all right, so I think we'll stop here, and this completes your unit 4. Okay, so from next class I'll be starting off with the final unit, which focuses on the power amplifiers. Okay, all right. So students, any doubts?